Hi everyone, I'm Madan Thapachetri. I am your TA for Water Resource Engineering 222. So today I will be discussing about some of the homework problems that were assigned for week 2. So let me go through the question number 2.4.4. So it is a classical fluid mechanics problem related to manometer, and it asks us to determine pressure in the pipe in psi and in inches of mercury of manometer, reading of h is equal to 3 feet. So basically we need to find pressure in pipe, that is here. So let pressure at this point be PA, whereas this above the mercury in this pipe section, we consider that as atmospheric pressure, so which will be equal to 0. And there is like some rule. Suppose this 1 and 2, they have the same elevation and they flow in the same fluid, so we can consider that as a reference line where P1 pressure 1 is equal to pressure 2. That is, we have mercury here, so pressure at this point will be same. So now let's go through some of the uh, key important uh, term that we will be using later. So for example, for first of all, like water specific weight, which will be equal to 62.3 lb, it is given. So we can determine a specific gravity of mercury, which is 13.6. So similarly, we can calculate a specific weight of mercury Hg, which will be equal to 847.28 lb per feet cube. So like I already described about this point 1 and 2. So in the horizontal line 1 and 2 on the left side, so pressure will be equal to P1 is equal to P atmospheric plus 3 times specific weight of mercury column. And similarly for P2, it will be equal to PA plus 2 feet, as pressure uh, will be added when we go down. Now we already know that P1 will be equal to P2, so we directly compute. Now since we already know P1 will be equal to P2, so 3 times 847.28 is equal to PA plus 2 times 62.3, which will basically give us pressure at 5 will be is equal to 16.8 psi. And for second part, we need to convert pressure to inches of mercury. We know pressure is equal to height of mercury times specific weight of mercury. Specific weight of mercury, we already know P pressure, so it will be equal to 2417.24 lb per feet square, whereas oh sorry, so pressure is equal to 2417.24, whereas we already calculate this specific weight, which will be equal to 847.28 lb per feet cube, which gives us 2.86 feet of Hg. So converting feet to inches gives 34.3 in Hg. So now let us go through question number 2. Since I already solved this problem, so you can just go through the solution, avoiding my voice. as well. So this question is about finding the stability of the dam at point A. It asks us to determine hydrostatic force, and also it asks about like center of pressure, and lastly moment check about toe A. So for this rectangular water surface area, we know that force will be is equal to specific weight of water times centroid depth times area. And for centroid depth, for a rectangular surface, it will be equal to height divided by 2, which will be equal to 4.5 meter. We know specific weight of water is equal to 9790 Newton per meter cube, whereas for calculating area, it will be 9 into 1, which will be equal to 9 meter square. So putting all these three in equation 1, we will get 3.96 times 10 to the power 5 Newton per meter length. So for finding the second part, that is location of force, center of pressure, since this is rectangular surface, uh, we can find center of pressure YCP is equal to centroid depth plus inertia of moment divide by area times as this is the formula. So since we already know center depth is equal to 4.5, whereas inertia of moment for rectangular area will be um, base times height cube divided by 12. So this gives us 60.75. So finally center of pressure or location of force will be 6 meter. I think up to here, there may not be any confusing things. So I will go into third part, which seems a little bit tricky. So we know moment, we need to find moment about 2A. So moment is equal to force times perpendicular distance. So since force tends to tip it over dam, so moment caused by water will be like force times perpendicular distance. That is here this 9 minus 6, because perpendicular distance from to A will be vertical, so it will be just 3 times force that we already computed in earlier first part. So for computing the writing moment from dam weight, so moment of weight of dam will be equal to weight times perpendicular distance. So for finding the weight, we know a specific weight of dam that is given as 2.78, and times volume. So for a specific weight of concrete uh, with respect to water, we need to have like multiply 2.78 into 9790, and for volume it will be 1 by 2 b into h times 1 meter, which is distance, area times distance. So that give us 5.5 into 10 to the power 5 Newton. And for right angle triangle, a lever arm from toe, that is dw, will be equal to 2 times b divided by 3, which basically give us 3. So hence, moment of inertia or moment of inertia at dam caused by weight of dam will be 5.5 times 10 to the power 5 Newton times 3 meter, which gives us 1.65 10 to the power 6 Newton meter. So now this gives us net moment. This helps us to check net moment. That is, net moment at A will be equal to moment of weight of dam minus moment of water. So that give us 4.6 times 10 to the power 5 Newton meter. So since net moment is positive, the dam is safe. So here I can go back. Maybe you already have the solution things, but maybe I'm wrong. I'm not sure about this, but in solution for base, they consider B is equal to 3, but our base as per question is 4.5. So I use 4.5 that give us 3. So so that we solve like question number 2 as well. Now let us go through question number 3. So it asks us to solve a horizontal finding the pressure drop in the pipe per kilometer length. So this is pretty simple. This question is pretty simple because uh, it just asks to find pressure drop. And if we know the Darcy Weisbach equation, then it will be pretty easy. So as the question says, minor loss are negligible, so we ignore minor loss, but there will be pressure drop because of friction with pipe wall. Like I already mentioned, we know Darcy Weisbach equation. So HF is equal to F L by D B squared divided by 2G. This formula is Darcy Weisbach equation. So we already know L, D, and we also know G. I have rewritten L in the form of meter section so that it will be easier for us to compute numerical. And I also rewrite Q is equal to 3.5 meter cube square per second, and diameter of pipe as 1.5 meters. So what we need to find? We just need to find friction factor and velocity. So since we already are given Q, so from Q we can use continuity equation. So Q is equal to area times velocity. So this gives us help us to find velocity, which is equal to 1.98 meter per second squares. So since we calculate velocity, we just need to find friction factor. So friction factor can be determined by using Reynolds number and surface roughness, relative surface roughness. So for friction factor, we need to check whether the Reynolds number is turbulent or laminar first of all. So we know like a formula for Reynolds number is Re is equal to dV by kinetic viscosity, and for water at 20 degrees Celsius, the kinetic viscosity is equal to 1 into 10 to the power minus 6 meter square per second. So that gives us the value for Reynolds number will be equal to 2.96 times 10 to the power 6. Since Reynolds number is greater than 4000, the flow is considered as turbulent. Similarly, finding the relative roughness E by D. So for commercial steel roughness, E is equal to tentatively 0.045 mm, and diameter is equal to 1.5 meters. So converting that into millimeter, that gives us 1500. So that is E by D is equal to 0.00003. So using Reynolds numbers and relative roughness, we can use Moody diagram for finding the friction factor here. So since like relative pipe reference falls under this line, whereas the Reynolds number falls this. So when we draw a line up to here, we can consider friction factor as 0.011. So since we already have friction factor F and we already have computed B, then it's just putting the numbers into the Darcy Weisbach equation. So that gives us HF is equal to 1.47 meter, whereas our main intention is to calculate pressure drop. So pressure drop and head loss are related by this formula. So density times G times head loss, that gives us this density times G is equal to specific weight of water times HF. So that gives us pressure drop of 14.4 kilopascal per kilometer. So now let's jump into question number 4. So here the question asks us to uh, find the discharge using Hazen-Williams equation only. So we are given this is typical two reservoir problem. The length of reservoir is 2.5 miles. We can convert that into meter, no feet. That gives us 13,200 feet. And we are also given like uh, elevation difference between surface of two reservoir is 395 feet. That is equal to head loss or frictional loss. Head loss. So we know energy equation to the pipeline. So this is the typical energy equation of the pipeline where HL will be equal to HF. So from Hazen-Williams equation, this head loss will be K times Q to the power M. So for K is equal to 4.73 L divided by D to the power 4.87 times C to the power 1.85, whereas this power M value is equal to 1.85. So this is also we can see from the unit section from our textbook. For commercial steel, maybe new or very smooth, value of C is considered as 150. So that gives us all the value, uh, and we just need to put in the uh, equation of K. So that gives us 0.0132. So our final, since we are already given HF, so that is 395. We already know value of K. We need to find discharge using Hazen-Williams. We know M value, so by computing, uh, just putting the numbers, we got Q is equal to 263 cubic feet per second. So now it's our maybe last question, fifth question. So it asks us to find pressure at this pressure tank. So the length of this tank and this upper part is 200 meter, and since this is exposed to this point to it as is exposed to atmosphere, we consider that as atmospheric pressure. We are given oil flow rate of 0.012 meter cube per second, and we are given diameter as well, 15 centimeter, and so we need to find air pressure. How much air pressure will be needed over this fluid to produce requisite like to go to flow from this pipe. So since there are some given like specific gravity of oil is also given, and this kinematic viscosity is also given, and this roughness value is also given. So Using the energy equation, let us compute. Let us just rewrite first pressure equation. No, energy equation. So which will be equal to this one. Since like this this is big tank, we can consider velocity as static. So B1 can be 0, whereas this P2 it is exposed to atmospheric, so we consider that as well 0. So that gives us P1 by rho plus 100 is equal to B square divided by 2G plus 106 plus HL. So this HL is the combination of major loss that arise from pipe friction plus minor loss, which is from entrance here. It is rectangular section. So using the uh, so for finding the HF, we know from equation of Darcy Weisbach. This is the equation. So we don't know F and we also don't know V, but we are given Q. So from Q we can derive velocity. So next step will be determining velocity and friction factor. So to find velocity, we have Q, I already mentioned. So these are some pre-processing for finding the area and some unit conversion. So velocity will be equal to 0.68 meter per second. So after like for I forget to talk about this head minor. So that is will be equal to Ke times B square divided by 2G for square is in trans, and value of Ke is basically 0.5. So since we already find B, our intention will be like we talk about, we need to find F. So for finding F in the previous question as well, we talk about Reynolds number and relative roughness. So we calculate Reynolds number. Uh, we are given like everything. We are given D. We are given kinetic viscosity as well, and we just put the number in the formula, and we got this 5.02 times 10 to the power 4 turbulent. Similarly, for relative roughness, we are given this E as well, value of E as well, and we have known D. So that gives us 0.008. So looking at the Moody chart again, so friction factor will be like 0.024, and you know how to use Moody chart properly as well. If not, I suggest you to look one of the YouTube video related to how to uh, look Moody chart. So now we already have friction factor, we computed velocity. So we just, what we are missing? So we just put everything in the previous equation. So this gives us like this form, and let us rearrange the numbers so computation will be easier. So I intentionally let like P1 by specific P1 by this row as on the left side, so it will be easier for next step. So after all the computation and computation of the computation, I got 6.78 meter of oil. Now let us convert that pressure head to pressure. So since specific weight of oil is equal to specific gravity times specific weight of water. Specific gravity of oil is equal to 0.84 times 9790. That gives us 8224 Newton per meter square. So pressure will be equal to specific weight times pressure head. So that gives us 55.8 kPa. So these times I rewrite already. Maybe next time I will try to solve along with you, so it will be easier for you to understand the concept as well. So thank you for listening this whole class. Uh, if you have any question, you can contact me in my office hour or lab time. Thank you.